So our first speaker is David Esseni. He's from the University of Udine. His career has gone from Bell Labs to Udine. He may know the book that he's co-authored, Nanoscale MOS Transistors, Cambridge University Press. He's a fellow of the IEEE.
Well, first of all, I'd like to thank the organization of this workshop, and actually got me here in Berkeley to give this presentation. As you've seen, the presentation is quite specific, and I've been asked to present, to give a snapshot of the our perception of the influence of interface traps on the performance on tunnel FETs. And since the topic is quite specific, I actually didn't actually arrange any long introduction, and just would like to go straight to the working principle of tunnel FETs, at least in its, I would say, maybe more conventional arrangement that is related to lateral devices, so source, gate, here in the channel region, and then drain. These devices, even in this arrangement, they work as we've already heard even in the previous presentation, as a density of state switch. And in fact, this is the configuration where you have you are in the off state. And so here, the density of states in the channel is much higher than the states available in the source, so your tunneling distance is very large. And that's the way you can switch the transistor on, just by pulling down the density of states in the channel, so that there is a tunneling window between the density of states in the source and the density of states in the channel. Of course, this switching on and off of the device is the key point. And it is quite intuitive, after all, that if you have some sort of spots of density of states in here that are related to possible traps, so density of states in the gap, this can be somewhat harmful to the working principle of the transistor and our ability to get actually a subthermal subfraction sweep out of these transistors. Well, actually, it's been explicitly claimed in the literature. For instance, I'm quoting from this paper by IMAC. It is mainly an experimental paper, that theoretically the band-to-band tunneling mechanism in tunnel FETs can offer subthreshold swings steeper than system level per decade. However, in practice, it is very difficult to obtain that at room temperature due to the undesirable trap-assisted tunneling mechanism observed in the off state. It's given as a sort of a fact in some of this paper, and that's by no means the only example. There are several papers, mainly experimental papers, notably, I would say, just claiming that traps is one of the main hindrances in actually the achievement of a subthreshold slope that is better than system level per decade. And I think that this is essentially the rationale behind the reason why I'm giving this presentation. And so I will essentially, first of all, address a few topics related to the physical mechanisms, mainly based on simulation results. So what has been actually claimed in the literature that interface traps can do to the performance of tunnel FETs. So in terms of leakage current, influence on the band profiles, that's mainly the things that we're all more familiar with because it's similar to MOSFETs. And then direct role in the transport, trap-assisted tunneling, and also as a possible source of variability. Then in the second part, I will just review some experimental data and experimental works that were just, focused on the possible experimental assessment of the role of actually interface traps in tunnel FETs. So, influence of interface traps on the leakage current and the influence on the band profiles. So this is a study carried out by our colleagues in Bologna, published a few years ago, and also, actually also in the second paper. Now I don't remember actually the affiliation of this author here. And what they have shown is that, for instance, for a very small VDS, when the band-to-band tunneling at the drain is small, And in these TCAD simulations, the leakage floor here was essentially due to a Shockley reed hole generation. If you increase the trap density, you essentially increase this noise floor, essentially because here interface states are considered as defects that enhance the conventional, let's say, Shockley reed hole generation. They do not have necessarily a big impact on the subthreshold slope, as you see here, especially for the not too large densities, okay? But for sure, acceptor type traps can also change, the band bending, as we will see better in coming slides, and they can affect actually the on current in here. The possible role on the electrostatics has been actually emphasized in this paper, and the fact that it is claimed here is pretty well known even in MOSFETs. And if we consider that in the upper part of the band gap we essentially have acceptor-like traps, so traps that once they get charged are actually negatively charged, then what we can envision is that if this black line here is the band profile, this is the source, this is a channel, with no interface states, if we have a dominant acceptor behavior of the traps, then for a given gate bias, we have less band bending here at the source channel region. And instead, if we have a positive charge and so dominantly donor behavior, we can actually have more band bending. And this effect of the interface states, so a sort of indirect effect on the tunneling through the band bending, okay? This indirect effect in this study here, that is again based on TCAD simulations, has been identified as the culprit of the fact that here you have in the on state, you have an on-current degradation in the presence of traps. Of course, whether you have an acceptor or a donor-like behavior, it also depends on the spatial and the energy distribution of the traps. It is quite interesting that if you think about the fact that the traps can have on the band bending, they not always and not necessarily have a detrimental effect on the IV characteristics. And in fact, again, our colleagues in Bologna pointed out in this paper that if we think instead of a case where you do have a relatively large drain voltage, so you have a drain voltage of 0.5 volt, and consequently you have a pretty strong band bending here at the channel drain region, and you consequently have a large band-to-band tunnel here, a consequently large ambipolarity, so in essence a behavior that you really don't want to have, but if the drain doping is large, this is what we actually tended to see in devices, even in experimental analysis, I mean. Well, in that case, you see that if, again, in black, you have the band bending with no traps, and in this region, even in the spacer, channel to drain spacer here, you have an acceptor-like dominant interface traps, then for a given gate and drain region, you can have a somewhat smoother band bending in this region, as we've seen in the previous slide. And this can also be beneficial for band-to-band tunneling. And in fact, in these IV characteristics that were obtained by using just a commercial TCAD, Centaurus, as far as I remember, you see that this is the curve that corresponds to no traps, the black, and that when you increase the trap density down to this huge, actually, concentration here, you somewhat reduce the band bending here at the channel and drain region, and you can have a beneficial effect on the ambipolar behavior here. Actually, the results that we discussed so far are mainly results, according to the outline, I would say, that have to do with the leakage floor and how it is affected by traps and the band bending. But these results have not a very strong, I would say, direct effect on the subthreshold slope. So, okay, well, it depends on how you measure it or how you define the subthreshold slope. Of course, it affects a lot the minimum off current that you can achieve, but this is a not big distortion, so to speak, of this region here. In the following set of slides, instead, I will try to address, to show phenomenologically, I would say, how actually traps can have a direct role in transport and how that can, in fact, have a more direct influence on the subthreshold slope. Let me first of all mention an experimental fact. Those of you who are interested to the thin oxide literature are probably aware of the fact that especially 15 years ago, around 2000, there is a huge literature concerning actually stress-induced leakage current in the thin oxides. At that time, the acronym was SILOC, and it was pretty famous and popular at that time. And a fact that's been systematically observed is something that is shown in this graph here from Professor Takagi, just because he's in the audience, but there is actually a big amount of data available in the literature. And here you see that this is the curve of the IV of the oxide virgin, and this is what you see after an electrical stress. Not only the current at small voltage increases dramatically, but even the steepness, if you wish, of this IG versus gate voltage decreases a lot. And this has been actually ascribed to a trap-assisted tunnel in traps generated inside the bulk of the oxide. So the question is, can traps somewhat assist the source-to-channel band-to-band tunneling and affect the subthreshold slope in tunnel FETs? We tried to address this question by using simulations, and in this case we used NEGF-based simulations. It was a few years ago. And as you see, this is the template device that we used, and it is essentially a nanowire, so a lateral device, a source, gate, and drain. And it is not trivial, by no means, to account for traps, not even in the NEGF simulations. And the approach that we used is somewhat phenomenological, in the sense that we describe the trap as just a cubic potential well that we can place everywhere at the interface or even in the bulk of the nanowire, even though I'm going to present essentially results for our trap placed at the interface. We had results also for the trap placed in the bulk, so to speak, or I should say the center of the nanowire. And what is interesting in this approach, although it is a phenomenological one, is that when you put this in the electrostatic and NEGF solver, you have all these possible effects that are, let's say, naturally taken into account. So, of course, this density of states here can be charged, and so you have an effect on the electrostatics. It can contribute to the transport. And incidentally, by changing the parameters that describe this quantum well here, we could actually play a little bit with the energy of the trap in the gap. So these are some of the results that have been published about 2 years ago. And for instance, this is an effect for a very narrow 5 nanometer nanowire. This is a trap here at the beginning, let's say, of the channel, a source gate channel region. And here, well, the white one here is the IV characteristic with no traps at all. And then you have different colors corresponding to a quite shallow trap, 60 millivolts below the conduction band, and then about 100, 150, and about 230, about 315 millivolts below the conduction band. And as you can see in this effect, at least in the current range that is probably most important for applications, we've seen that the largest effect seems to be actually due to relatively shallow traps. And The following slides try to explain why this is the case, according, of course, to the model. So, according to the model, what happens is the following thing. Here, again, the white line is the IV characteristic with no traps, and the yellow one is the one that had the largest effect with relatively shallow trap. If you go to very small VGS, negative VGS down here to very, very small current densities, you see that this is a picture in the top, in the A, let's say, picture. This is the density of states inside the source, the density of states in the channel region. And this spot over here is the density of states in the NEGF formalism given by the trap. And you see that if you think that the current density is more or less maximum, let's say, around the Fermi level, that incidentally here is conventionally taken as a 0, so 0 is the Fermi level at the source, you see that the trap is too high in energy to significantly contribute to the current. And so the effect on the IV is essentially negligible. But if you increase the voltage and then pull, of course, both the bands and the trap density of states down, then the density of states of the trap just happens to be in the tunneling window. And when it is in the tunneling window, it can actually affect the transmission quite significantly. And in this case, since we also had the phonon scattering in, we've seen that actually the dominant path is an inelastic tunneling through the trap, so mediated. The trap acts as a stepping stone for the tunneling and actually remarkably increases the current. But if you then move to a much larger VG, let's say in the on state, then you have completely pulled down the density of states in the channel. You've opened the tunneling window that does not need any trap assistance, let's put it this way. And so the current is completely dominated by the source to channel region with no, 2 minutes, it's fine. Of course, since these traps can have an effect that depends quite significantly on the position and the energy of the trap, they can also contribute significantly. They can be a source of device variability. And we also explored this in our papers, and this has been also studied by other authors. And what we have actually seen is that traps can significantly contribute to a dispersion of the off current and the subthreshold slope. Yeah, just 2 quick slides concerning the experimental analysis. So is there an experimental demonstration or support of these possible effects of the traps? Here I would like to show just to mention 2 experimental, let's say, studies. The one have been carried out at Jülich, and in this case, we see that the black line here is the trap. It is based on pulsed IV measurements, and the rationale behind this is that if you have finite capture and emission time, then when you go to pulsed IV, you can have significantly different IV compared to the DC ones. And actually, this is the difference. And if you look this in terms of threshold slope, you can probably see a significant difference from the, say, 100 microsecond pulses and 10 microsecond pulses. But these are the original IVs, and it's up to you, actually, to judge how big this effect is. But actually, shallow traps can have extremely fast capture and emission rates, and this measurement is very challenging. And essentially, the last slide is about a study, an experimental study carried out in IMEC. And what they did is just to have an electrical stress of their samples. And with the electrical stress, they can actually increase the density of interface states, but they could not see any significant effect on the subthreshold slope. But in this last case, let me just say that you see that they essentially started with samples with a subthreshold slope that was larger than 200 millivolt per volt. So this brings me to the conclusion, and this was the starting point of this presentation. Traps perceived as a serious hindrance to the development of tunnel FETs. And unfortunately, in 3,5 materials are known to have larger trap densities than group 4 materials. Several mechanisms for trap-induced performance degradation have been discussed in the simulations, but according to my understanding, there is no clear experimental evidence, no compelling experimental evidence that this is the main source of subthreshold swing degradation. Thanks a lot.
Okay. Thanks very much.